what we're going to do now is just a bit on review of the integration by parts. Yeah. Okay, so what we're going to do now, right, is on the review of the integration by parts. Right, I'm sure you have done this before. Right, for the formula for the integration by parts, we're going to use this very often, right? Because it involves integrations. Right, what we have to remember is that, right, when we do integration by part, just like this, right, is the product of two integrals, right? We have u and dv, and this is the results of integration by parts, right? U dv is equals to uv minus v du, and we chose u according to this rule, whereby we have the log exponentials, right? Right. Algebraic expressions, trigonometric expression, and exponent. Sorry, it's not. It's inverse trigonometric expressions. A for algebraic expressions, T for trigonometry, E for exponentials. Right. So, what we want to do now, and I hope you realize that when we do integration by parts, let me open another file. See, when we do integration by parts, just to remind you that when we have this, right, the formula starting with this, u dv is equals to uv minus v du, the integrals of v du. Right? An example is that when you have, see, I don't show you the one that I had in the lecture note because that is a bit more difficult. But when we look at this, say that you have, even when with the simple expression ln x dx, right? How do you integrate this? I hope you realize that this can be regarded as the integrals of 1 times ln x dx. So what you have to do in this case is a product of two functions, right? One function is u, the other function is dv. So how do you choose u? U, according to the rule there, you have to use, first you must define, the first preference is log, inverse trigonometric functions, algebraic functions, trigonometric functions, and exponential. So what we have there is the log. So what we have in this particular instance, Right. So what we want to do there is to choose u as ln x, and then the dv is 1. All right. Can then everyone understand why we choose u as ln x and then dv is 1?
Yes.
Okay. Can I choose u as 1?
Cannot.
Cannot, right? Because what we have there is two functions between log and algebraic functions. One is algebraic expressions, so you cannot choose u as 1. So what you want to do, when we apply this formula, the easiest way is to use tabular integration. So when you do tabular integrations, we divide it as u and dv, right? So this is a table, right? Here we choose u as ln x, and then dv is 1. So on this part, we're trying to differentiate until you get 0, if you can get 0. Right? So what you have there, if you differentiate this, what is the derivative, right? On the left-hand side here, the first column, you differentiate ln x, it will be 1 over x, isn't it? Correct?
Yes, sir.
Yes.
What you have there, and then we differentiate this, because this is equals to x power minus 1. So if we differentiate once again, what do we get? Minus x raised to power minus 2, isn't it? And it goes on and on. But then again, when we integrate this, something is not right. So what we have in this particular case is that you, wait a minute. Doesn't work. It doesn't work because what we have there, if we integrate this, it will be x. So it will be x. Oh, it doesn't work. Doesn't work. Sorry about that. If I just doesn't work. So I repeat the process again. If I have the integrals of u, right, the integrals of ln x dx, oh, it doesn't work. Sorry, it doesn't work. If we look at x, say that x ln x dx. So what we have there is we have algebraic expressions and log. No, I think I just put an easier way. I just put an easier way instead of log here. We have exponentials, if we have exponentials of x there, x e to the x, so we have two functions, which is algebraic explanation and exponential functions. All right, so we're going to let u and dv. All right, so u, we're going to, according to this, u is obtained, and the first pattern is according to this. So we have algebraic and exponentials. What we have there, so that means we choose u as x, the dv is e to the x. So therefore here what we want to do is to differentiate this until you get 0. So you have x, we take the derivative of x, it will be 1, take the derivative of 1, it will be 0. Then in this, in the second column, we integrate. If we integrate, it will be e to the x, e to the x. Then the next part is, right, what you want to do is to have a plus or minus, an alternate plus or minus. And it's an alternate plus or minus there. So it should be minus. Right, so what we have there, the integrals of this, x e to the x dx there, will be equals to, right, the first one there will be x, you take the according to the arrow there, it will be x e to the x minus the integral there which will be a product of this and this, so it will be minus e to the x dx. So that means it will be just x e to the x plus e to the x dx. So in the end, we can simplify this as x e to the x plus e to the x plus a constant. Right, can you understand this?
Yes, sir.
Boleh kan? So what we want to do in the right, in the what I want to do in these examples that I have, right, in the examples that I have, there is same thing, right? We want to integrate. We want to evaluate this x squared x minus 2 squared cos n pi x over 2 dx. So what you want to do, because we have to do this several times. If you use the above one, if we use this, you can. But to make it easier, we use tabular integrations. So here we choose u to be, x minus 2 squared. Then we differentiate the expression until you get 0. Right, so what you have in this case, if you differentiate x minus 2 squared, it will be 2 into x minus 2. Then we differentiate this, it will be 2, isn't it? Because that is equals to 2x minus 4, isn't it? So if we differentiate 2x minus 4, it will be 2, isn't it? Then the next line here, if we differentiate 2, it will be 0. See, on the other parts, on the other column, we integrate, right? Here on this part, on the second column, we integrate. So here we integrate cos of n pi x over 2. Please remember that when you integrate this, right, the integration of cos x, so that's too big. Right, the integrals of cos kx there, if we integrate this will be 1 over k times the integrals of sine kx. Sorry, what am I doing? Right, the integrals, right, the integrals of cos kx there, dx will be equals to 1 over k sine of kx plus a constant, isn't it? So that's why we have 2 over n pi sine n pi x over 2. And we integrate this once again. So we have minus 4 over n pi squared cos n pi x over 2. Then in this line here, we have minus 8 over n pi cubed sine n pi x over 2. Then the next part is to have alternate plus or minus. So it will be plus there, minus and plus. Then what you want to do, when as a result of this, you're going to, the first expression is obtained by taking the product of this, x squared, x minus 2 squared, right? And 2 over pi sine n pi x. So that's the first one. The second one is obtained from this. So it will be, is 2 times minus 4, right? That will be minus and minus, so it will be a plus there. So it will be 8 over n pi squared, x minus 2 cos n pi. And you have the third expressions over here, right? In the third expression, it's 2 times minus 8, so that will be minus 16, right? So what you have in this particular case, I take a shortcut by substituting x equals to 2 there. See, the first one there will be 0, isn't it? If you substitute x equals to 2, right, it will be 0. That one is also 0 because when you substitute equals to 2, and that leaves you with just 16 sine 2 n pi over 2, sine n pi, isn't it? But at the same time, sine n pi is equals to a 0. Sine n pi, you should realize, oops, sine n pi is equals to a 0. So that's the result. When you substitute x equals to 2, everything is 0. And when you substitute x equals to 0, see the left hand side there, when you substitute, I just erase this, right? When you substitute x equals to 2, everything is 0. That when you substitute x equals to a 0, when you substitute x equals to a 0, what happens is that this will be also 0 because you have sine 0 is 0. This is also 0. So we have, again, it will be 0. So the only thing that is left is this. When you have, when you substitute x equals to a 0, you have sine cos of 0 there. Cos of 0 is 1, isn't it? And then that leaves you with 8 times minus 2, which is negative. But remember, it's the because of the negative in the, that will give you a positive. You have to work it out on your own. Boleh ikut tak?
Boleh sir, boleh.
Okay, so you work it out. It's quite a long way to do this before you reach this, right? But you have to do the substitutions carefully. Now, in these examples, right, on this integration by parts, evaluating e to the x cos x, sama juga, where here you choose u as cos x, dv is e to the 2x. So when you are doing this, now this time around, when you, because you have exponent and trigonometric functions, right? And here you choose t first, u as trigonometric function. There's no way that when you differentiate, you will get 0. Right? There's no way when you differentiate, you get 0. So you stop differentiations when the original function is being repeated. Right? Because we originally starts with cos x, finally we have cos x then. So you stop at that point. See, on this side, in the second column, you integrate. So you integrate until you get the third line there. And it is critical there. When you are doing this, this is the obtained when you are combining this one. That's the first expression there. This is the second expressions, right? But when you come to the third expression, when you combine this, you still have to maintain the integral. Right? You still have to maintain the integral there. And please keep in mind this one here. I just have to erase this so that it will be a bit clearer. What happened in this particular case is that, see, when you have this, when you have the integrals there, it's being repeated, e to the 2x and then e to the 2x cos x. It will be the same thing, isn't it? So you bring this to the other side. So what you have there is that in this line you have 1 plus 1 over 4, isn't it? 1 plus 1 over 4 on the left-hand side is 5 over 4. And you have that. So this one here, if you bring this to the left-hand side, boleh ikut tak?
Boleh sir, boleh.
Okay. So once you've got this, you just simplify this part here. So when you simplify this part, this expression here, that will be 0 because sine pi is 0. Please keep in mind, sine and pi will be 0 for all n. When n is integer. But cos and pi cannot be 0, right? Because cos 0 is 1. Cos pi is minus 1. So what you have there is that this will be 0, this will be 0. So that leaves you with this expression, the first and the third expressions. Each power of 0 is 1, cos 0 is 1. So you have just a half there. But remember, you have to multiply it by the 4 over 5 there. So that means when you simplify, it becomes this. Right? Cos pi is equal to minus 1. Right? Please remember that cos pi is equal to minus 1. So that's why we have these expressions. Okay, boleh faham?
Boleh sir.
Okay, kalau boleh faham, you do it yourself. So this is the review on the integration by parts. Now next, what is important is on the full range Fourier series. On the full range Fourier series, what we are doing, because what we have, to go back, what we do, right, in this one here, right, we have, in this is again, right, please keep in mind that in this chapter, kita cuma sebenarnya sikit je, we only look at the full range Fourier series and half range Fourier series with some possibilities, with some variations. So only 3 parts in the chapter, tak banyak kan? And right, on the full range Fourier series, we are only using this formula. Right? A Fourier series is a way of representing a periodic function as an infinite sum of sine and cosine functions. Right? We can have a Fourier series of an expressions if the function is periodic. What is meant by a periodic function? That means there is a repetitions. of a functions. That means we can recognize one cycle, just like the cycles of day and night, right? Day and night is considered as one cycle, is a routine cycle. Another cycle is 1 week, right? 1 week you have starting from Monday, Tuesday up to Sunday, right? Or some people say the first day is Sunday, right? So Sunday, Monday, and up to Saturday, isn't it? Where generally the Saturday is considered as the seventh day. Sunday is considered as the first day of the week. But it depends, because we only in our case, possibly we consider Monday as the first week of the week, because that's the first day of the working day. Now, what we have when we have periodic function, because there are many phenomena in this world where we can have cyclic behavior. So that's where Fourier series is important, because whenever a functions has a complete cycle, just like the cosine and cosine functions, right? It is we can see one complete cycle. So we can express functions in terms of series of sine and cosine functions, where you have an in this particular case, right? An, right? This is the Fourier series representations of a periodic functions. L is actually related to the period of the functions, where you have a naught is equals to 1 over L, and we have to integrate between from minus L to L f of x dx. An is this 1 over L times the integral from minus L to L f of x cos n pi x over L. Right, so what we have in this particular case is that we have this right, we have Bn is 1 over L keeps on changing. I cannot put the highlights. Okay, never mind. What we have there is that we have Bn, right? And then we have, right, this is one examples whereby, right, the functions can be considered as one full cycle. Sorry, I have to, I'm just wondering why it keeps on. Right, so what we have in this particular case is that when you have An, right, it's just a matter of using this formula to find the Fourier series, right? And these examples in this particular case, right, what we have there, I just put two examples whereby we have two and examples of periodic functions, right? So this is the length of one complete cycles over here, right? When you have this is one complete cycle. Notice that the function is being repeated, being repeated from minus L to L, and then from L to 3L. Same thing in these examples. The function is this is just a simple function. From minus 3L to minus L, you have a straight line here, and it's being repeated again from minus L to L, and then again it will be, the next one will be over here, it will be 3L, isn't it? Right, on over the next interval. So the period here is given by 2L, right? And both function has repeated pattern within the period of 2L. Now, why? This is the reason why we use Fourier series representation, because it allows us to predict the behavior of the solutions for a given differential equations. Right? Because what we want in mathematics, what we want is to have a predictions. Most of the time is not accurate, but we have some idea what will happen in the future. And most of the time it can't be accurate, but at least we have some idea. So that's why Fourier series analysis is important. And most of the time when we use Fourier series analysis, to reduce the noise in digital processing, right? In the era of digital age, we have to make use of Fourier series representations to reduce the noise. Now, what is meant by a periodic functions in this case is a function is periodic if there exists a positive number p such that f of x plus p is equals to f of x for all x in the domain of f. And p here must be positive. Right? So that is the definition of periodic functions. So in this case, if we look at f of x as sine x, right? This is the graph of sine x, right? So you can see that one cycle here is one complete cycle is from 0 to 2 pi, and the function is being repeated over and over again, right? For the for an interval of 2 pi. So you can see that the basic pattern is there being repeated from 2 pi to 4 pi, and then from minus 2 pi to 0, from minus 4 pi to 2 pi. So what we have in this case, right? Sine of x plus 2 pi is equals to sine x if you expand this. And this means that p is equals to pi. And sine, at the same time, sine x plus 4 pi is also equals to sine x. So therefore, p is 2 pi, and so on. But the least positive value there is 2 pi. So therefore, we make 2 pi as the period of sine x. And you can see in the same examples, when you have f of x equals to cos x also has periods of 2 pi. So what I want to do in these examples, in examples 2, is to find the Fourier series of these periodic functions, given f of x is a piecewise continuous. There is only one there. Right? The complete cycle of a function is 1 from 0 to 2, and then from minus 2 to 0, it is given by x. So sketch the graph of the functions for the period of x from minus 4 to 4. So what you want to do in this particular case is that to get a straight line. So remember that when we did Legendre polynomial, we have a piecewise continuous function, isn't it? Right, where we have the function is being split within an interval. So in this particular case, the basic functions here, first you need to highlight the for interval between -2 to 2, right? And the function is equals to 1 when x is between 0 and 2. And the function is equals to x when x is between -2 and 0. So this is being repeated over and over again over an interval of time. So if we want to sketch the graph between -4 and 4, the same thing is being repeated. See, I hope you realize that. See, on the left-hand side there, we pick the interval. Right? You have to remember that. Right? When you are doing this, right? This is, we started within 0 and between -2 and 2. So that means this one you cannot have, right? This one here should be the repetitions of that one there, isn't it? And the next one here, we just shift this to the other side. So that's why we have these functions. I hope you can understand this. Boleh faham tak? Hello?
Boleh sih.
Hello?
Boleh.
Yes, sir.
Right, so what, I don't know why some students have difficulty finding this, but if you remember, this is the basic functions. Right? This is the basic function. So that means if we shift the whole thing onto the next interval, we will see the left-hand side of this, isn't it? And if we shift the whole thing on this one, we will see this. Okay, so that's the sketch of the graph. Then the next one, what we want to do is to find what is the Fourier series. So we are just applying the formula I've shown you earlier, right? And it's just a matter of this, right? The formula in this case is this. And the most important part previously is that, please keep in mind, is to identify what is L. Please remember that L is, 2L is equals to 4, isn't it? So therefore, L is equals to 2. So if you fail to recognize this, everything goes wrong. So please keep in mind, determining L correctly is the most important part in finding the Fourier series. So in this case, we just apply the formula, just substitute L equals to 2 into the formula. So it's a half times the integral from -2 to 2 f of x dx. Now when it comes to this, remember we have to split the integrals into 2 parts. So the integrals is from -2 to 0 x dx, and then the other one is a half times between 0 and 2 1 dx, because we have f of x is defined equals to 1 for x between 0 and 2. And then it will be x when x is between -2 and 0. And please keep in mind, the 0 is included, and I did not highlight this. Right? Dalam ni, please keep in mind, this one here, right? When I draw this, you realize that at 0 it is a solid line, and on this graph here, and then it will be hollow there at the top line. You have to keep in mind why I put this. Right, please keep in mind. Right, here you have a solid one there. This is a hollow, right, because of the definition there. Here, when x equals to 0, the point is included. Okay, so that's so now we are just splitting the integrals there using the definitions, and then here the only thing that you can do this integration by part is the first integral. So you just follow the integration by part in the first integrals, and at the same time you just simplify this, right? It's just a matter of trying to solve this, right? So what you have there, you simplify it according to this, and then Bn is the same thing, just applying the formula, and then use integration by parts in these integrals there, and then you have to do it carefully, right? And hence you get the Fourier series expansions, right? Ada soalan tak agaknya? Because you can only do this, you can only understand this once you do the substitution, because you have to remember that sine 0 is 0, sine n pi is also 0, but the cos, when it comes to cos n pi, it won't be equal to 0. So I think the next part, I will post you the notes afterwards, right? And this is one exercise that you have to do, right? This is just a simple exercise. I hope you can do this one simple exercise. Probably, right? In this particular case, the curve sketching there will be a bit tricky. Agaknya boleh tak draw the curve tu? Boleh tak agaknya? Hello? Is everyone there? Is everyone listening ataupun senyap
Yes, sir.
saja? Boleh
Ada,
tak
sir,
sketch
ada.
the graph? Ya? Boleh tak?
Oh, boleh, sir, boleh. Kena try buat
Boleh.
dulu, sir.
Okay. So, okay. Itu sahaja untuk hari ini, and please keep in mind, untuk minggu ni, ini sahaja lecture. Sebab apa ni, dia ITM ni gatal. Masa you all ada break tu, dia tak nak buat khusus. Sekarang ni pula tergege dia nak buat khusus, and I cannot. Tak boleh nak buat apa. Asyik je lah dia kata dia suruh buat recording, and I think this is it. You have to learn it on your own at the same time. Saya akan cuba jawab lah your questions while you are doing this. So anyway, now I'm going to take the attendance.